In this lesson, we will explore and understand the characteristics and properties of different parent functions. Well, what is a parent function? In mathematics, every function can be classified as a member of a family. Each member of a family of functions is related to the simplest or most basic function sharing the same characteristics. This function is called the parent function. Now, if you recall, in grade 9, we explored the linear function. In grade 10, we explored the quadratic function. In grade 11, we are going to be exploring many more, starting with the square root function, the absolute value function, the reciprocal function, and later on in the course, we will be exploring the exponential function as well as the sinusoidal function. Now, with all these functions, we need to really know and understand the characteristics of each of their parent functions. So the simplest, most basic form of that function. So let's investigate. Given the following parent functions, complete each table of values, plot the points, describe their special features, and state their domain and range. Reminding again, domain would be all the possible values for x, range, all the possible values for y. Now, the linear function. The parent function for the linear function is f at x is equal to x. Let's then complete the table of values. If the input is -3, the output would be also -3. If the input is -2, the output would be -2, -1, input 0, output 0, 1, 2, and 3. Now plotting that, always x first, so x is -3, y is also -3, x is -2, y is -2, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Now, taking our ruler, making sure to connect plotting all the points properly, connecting them, arrows on both ends, and don't forget to label. F at x is equal to x. Now I want to point out, notice, this is our origin. That's a pretty important point. It's where all 4 quadrants meet. All right, so again, this would be quadrant 1. And labeling going counterclockwise, this would be quadrant 2, quadrant 3, and quadrant 4. Okay, these 4 quadrants create our grid. So we know vertical axis is always y, horizontal is x. Special features. Well, looking at what we have here, the parent function for the linear function f at x equals x is a straight line. So we can say it's a straight line that goes through the origin, that point 0, 0. Another thing we can show is that it does only go and remain in quadrant 1 and in quadrant 2. So we can say graph is only in quadrant 1 and quadrant 3. Okay. The slope, if you recall, slope is rise over run. So with the slope, my rise is equal to 1, my run is equal to 1. So my slope in this case, slope is equal to is 1, which is that m value. Okay, the domain. Domain, again, are restrictions or all our possible values for x. In this case, because our linear function, it does keep going as we saw with others, there are no restrictions on x. So we can say x is an element of real. The range, likewise, y is an element of real. Okay. Moving on, the quadratic function, which we did explore in grade 10. The parent function for the quadratic function is f at x is equal to x squared. So when the input is -3, -3 squared we know is +9. Negative 2 squared would be 4. Negative 1 squared would be 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. Now plotting that, when x is negative 3, y is positive 9. When x is negative 2, y is positive 4. When x is negative 1, y is 1. 0, 0, 1, 1, 2 and 4, 3 and 9. Now, again, we don't connect the dots. What we want to do is make sure that the graph is a parabola. Now, with a parabola, it's a nice, smooth, U-shaped curve. F at x is equal to x squared. Now, special properties about this quadratic function, of course, is that vertex. In this case, it is 0, 0. There is equation of axes. Well, that's a special property of any quadratic function. It is symmetrical about the vertex. Okay, meaning I can cut that right in front. If I had one of those plane mirrors and I put it on the vertex, the parabola, there would be reflections of each other. Now, some special features of this specific parent function for the quadratic function, which is f at x is equal to x squared. Now, parabola, definitely, it's a parabola that opens upward. The vertex is at the origin. And we know the origin is that point 0, 0. Now, in this case, we spoke about the quadratic function where the vertex is the most critical point. As you can tell with the parabola, it's decreasing. It gets to the vertex and it changes direction, starts increasing. So with that in mind, the vertex, the y value of the vertex is going to be the minimum, meaning the absolute lowest point on this parabola. So y has a minimum value. Okay, the axis of symmetry, I spoke about that. The axis of symmetry is that vertical line that goes right through the vertex. Is the y-axis in this case. It happens to fall on the y-axis. That is x equals 0. And in this case, for the parent function, the graph is only in quadrant 1. So remember, and quadrant 2. So graph is only quadrant 1 and quadrant 2. Looking at the domain, what are the possible values for x with the quadratic function? X is an element real. There are no restrictions on x. There is a restriction, however, on my range. There is a minimum, meaning that our y's values can be anything. However, they have to be greater than or equal to 0. Now again, or we can express it as function notation as in real, where f at x is greater than or equal to 0. Okay, so those two functions we have explored. We're going to be introducing a new function. We've seen this button before, or this on our calculators, the square root. Okay, so looking here, we're going to be exploring the square root function, and it's often called the radical function. Now, the parent function for the square root function is f at x is equal to the square root of x. These are the points that we are going to be using. Notice the input values. X is equal to 0, 1, 4, and 9. Those are actually chosen because those are perfect squares. To take the square root of a perfect square, you're going to get a whole number. The square root of 0, if I inputted x being 0, the square root of 0 would be 0. If I input the square root of 1, the square root of 1 is 1. If I input 4, the square root of 4 is 2. The square root of 9 is 3. So these points are very critical. In in further lessons, we will be doing different transformations, and we're always going to start with the parent function. So it is very critical that we know the key points for each parent function as well as any special features. So to graph this, 0, 0 would be my first point, 1, 1, 4, and 2, 9, and 3. Okay. Notice my function begins at the origin. F at x is equal to the square root of x. Okay, it does keep going, and what we would choose for the next x, or input value, would be another perfect square. So something like 16. The square root of 16 is 4. 25. The square root of 25 is 5. But we don't need to go through all those points. These are the 4 key points that we need to know for the square root function. What are some special features? Well, there is no symmetry here, so shows no symmetry. Okay, graph is only in that first quadrant. Graph is only in quadrant 1 and starts at the origin, which is 0, 0. The domain. Now it starts at 0, 0, and then it increases. So there is a restriction there. It's never going to have a value less than 0. So in this case, the domain x is able to be anything. However, it has to be greater than or equal to 0. The range, same idea. It starts at the origin and then the y values increase. So we're going to say f at x is an element of real such that f at x is greater than or equal to 0. Or if you want to use y is an element of real such that y is greater than or equal to 0. Keeping in mind f at x and y are interchangeable. Okay, moving on, we have the absolute value function. This is a new function. It is very similar to the quadratic function. The absolute value function, by definition, absolute value is the distance of a number from 0 on a real number line. So if we looked at -3, so if we look at -3, which is here, the distance from -3 to 0 is 3 units. And then the distance from is also 3 units. The absolute value is actually, I'm going to just put a note, a mathematical operator that makes a number positive. Okay, so what that means is if we took the absolute value of -3, -3's distance to 0 is 3 units. Likewise, if we look at +3, 3 is also 3 units away from 0. So with that in mind, any number that you put into the function, the absolute value function, when you take it out of the function, it is always positive. So the absolute value of -3 would be 3, because -3 is 3 units from 0. -2 is 2 units. -1 is 1. 0 is at 0. So 1, 2, and 3. Now, plotting this, we have at -3, we're at +3. -2, we're at 2. -1, 1. 0, 0. 1, 1. 2, 2, 3, 3. And we can keep going. We always want to use our rulers. And when we connect, it would be arrows, because of course there are different values of x we can input. However, arrows on both ends. Okay, so what are some special features? Now, like the quadratic function, this function, the absolute value function, also its vertex is at the origin. So vertex of graph is at the origin. This is also a symmetrical graph. If you can see right through at x equals 0 is the axis of symmetry, which divides the graph into two congruent halves. Okay, in this case, if we can tell, just like the quadratic function, our graph is only in quad 1 and quad 2. So we can express that as well. Graph is only in quadrant 1 and quadrant 2. The other thing we can know is the x and y intercepts are both 0. So the x-intercept and y-intercept are both 0. So again, these properties are very similar to the quadratic function. So with the domain, again, the function just keeps going. So we can say x is an element of real. The range, however, there is a restriction, meaning our y values are always going to be greater than or equal to 0. So we can say f at x can be any number. However, f at x has to be greater than or equal to 0. Or if you'd like to use y is an element of real such that y is greater than or equal to 0. Okay, moving on to our last function. This function is called the reciprocal function. A reciprocal function's parent function is f at x is equal to 1 over x. Definition. What we're going to learn in this function that we have something called an asymptote. An asymptote is a line that a curve approaches more and more closely but never crosses. It's almost like a border. Okay, you get close to it, but you don't ever cross it. In the function f at x is equal to 1 over x, the x-axis and the y-axis are the asymptotes. So when we draw asymptotes, we actually draw them as dotted lines to kind of give an idea that the graph will be approaching these lines, but will never cross them. So I'm going to just start with those asymptotes. I like to draw them in different colors so that we have them. Okay, oops. Try our best. Those asymptotes, no. Okay, so I'm going to try that again. So we have f x equals 0, and then we have the horizontal asymptote with y equals 0. It's always best to start there, and then we know our points will be falling between those asymptotes. Now, if we were to substitute x being negative 3, so their input is negative 3, our output would be negative 1/3. To substitute negative 2, we substitute that 1 over negative 2, which is negative 1/2. Input is negative 1, substituting that into 1 over negative, into x would be 1 over negative 1, which we can simplify to negative 1. Now, if you were to substitute 0, we know that 1 divided by 0 is undefined. So this is actually where we would have our asymptote. It is undefined. That means the function is undefined at that point. It doesn't exist. Substituting 1, 1, 1/2, and then 1/3. So to plot these points, we have at -3, we're at -1/3. At -2, we're -1/2. At -1, we are at 1. Likewise, at 1, we're at 1. At 2, we're at 1/2. And at 3, we're at 1/3. Okay, what are some special features? The graph is symmetrical about the origin. The graph is symmetrical about the origin, which means if I was to draw the line y equals x, I'm going to try doing that. You will notice that it is symmetrical. That would be so y equals x, just to show that it is symmetrical. Okay? That means these are direct reflections of each other. Okay? Notice that, and it crosses through that 1 and 1. Now, with that in mind, we can explore that the graph is only, so the graph is only in quadrants 1 and quadrants 3. 1 and 3. Okay, so now because we do have these asymptotes, like we said, asymptotes are a line that a curve approaches or a graph approaches, but it never crosses. With that, our domain then would have a point where our function doesn't exist. So that's called a restriction. So that means x can be any value, but it doesn't exist when x is equal to 0. So to put that in set notation, we would say x is an element of real. However, it can't be 0. It can be any other number. It's easier to say it can't be that value, which is where the asymptote exists. Y, f at x, is an element of real, but f at x cannot equal to 0. Okay, so since the graph cannot cross the y-axis, x equals 0, we call x equals 0 the vertical asymptote. Since the graph cannot cross the x-axis, that is y equals 0, we call y equals 0 the horizontal asymptote. The asymptote is a boundary where the curve approaches but never crosses.